Very much.
Okay, thank you. So this is jointly done with Christophe Ringeissen, who is also in the audience. And his work supported by the Swiss National Science Foundation Postdoctoral Mobility Program. So actually, it's nice that we were in this combination kind of session before, the talk before and the talk after, I guess, are about combination problems. But my motivation, at least, is more coming from wanting to understand and basically come up with new solving methods for array reasoning. And so this is an important topic in software verification. And it was very early realized that first-order reasoning techniques have difficulty dealing with it. And so basically the pattern since the original works of Floyd and his students has been to say, okay, we abstract away certain quantifiers. We introduce new, basically new signatures or, and then we develop decision procedures for them, right? And here, well, I focus in what I call parametric array theory. So they start from the simple concept of power structures. I will refer to them next. But then you can apply composition methods to get more expressivity. And so, yeah, so we basically have some semantic motivation, comes from model theory. So in model theory, you study basically models of functions, spaces, right? So here, MI are functions from the index at I to M, and then you have relations, not just one, but you could have functional relations that are interpreted point-wise, right? So you could say that the relation on a tuple of arrays holds if and only if it holds in every component. So basically, you can think of this as vector addition, for instance. And the nice point for verification for people that like to have theories where you can specify unbounded concepts, let's say, is that the index set here is arbitrary, right? And so Mostowski showed that, well, I mean, he realized that this structure here doesn't have quantifier elimination. And so the idea is that, okay, I need to extend the language. And so you can add these kind of relations here to do that, which are basically sets of indices where some first-order formula doesn't holds, right? And as I said, once you have these kind of set interpretations, then it was very natural for them to use the methods of Skolem to solve things like Boolean algebra on sets. And if you study how you reduce this theory, then you also can get to the question of cardinalities of sets, but you could also, as I said, combine with using this composition method with automata, and aggregation is something like summation over your array, right? So that's very useful for things like databases. And now the question I'm looking at is how do we automatically reason about this? Okay, so what methods of automated reasoning? So model theories look at the theory of a structure, but automated reasoning will really look at the syntactic theory, and so you can have more models. It's a different problem. And today I look at basically how you can combine data structure decision procedures with decision procedures for different element and index theories, which in fact was the motivation for polite theory combination in the time. And maybe to give you a glimpse of what are the problems, I guess, is, okay, so this thing to the right is the so-called combinatorial array logic. So this is implemented in set3 and was presented in a paper 2009 by Demora and Jotner. And essentially we have one of the nice things of this theory is that you can interpret their theories of sets and multisets. And so you view sets of arrays from some index domain to 0, 1 domain. So 0 means the element or the index doesn't belong to the set, and 1 means that the index belongs to the set. And if you want to think about multisets, then it's going to be an array from an index set to numerical domains where the number in the numerical domain is telling you the multiplicity of the element. So using that view, you could say, okay, the empty set actually is just the array that we have, which has all zeros. Okay, so this K operator gives you the array, right, from the zero value. You could, I don't know, implement union, let's say, right? So you could essentially say, point-wise, I'm going to look at my array, my representation of set as arrays, and I'm going to see, well, if I have a 1 and a 0, then okay, I have that element in the union. If I have 0 and 0, then okay, none of them is then, so I should output 0, right? And you can implement the rest of the operations like this. And now comes the question, right? So the issue is that okay, you may have a decision procedure for combinatorial array logic, but then you're instantiated to the element theory that has 0, 1 as a domain. And it turns out that you cannot use Nelson open combination method because you require extremely infinite theory. And so this is, there's something motivation. What can we do about that? And the idea is to use polite theory combination, which partially leaves the restrictions of Nelson open. And there is a caveat, which is that, okay, we still have the disjointness condition, so we cannot really have the element theory using symbols that appear in the maps. But there's still interesting questions in the disjoint setting. So one of them is politeness of sets with cardinalities, which was open in the work of Cachispa and Sal and collaborators from the CVC community, I guess. The second question is, okay, even in the disjoint method, how far can we push the method? And as an alternative that we have explored in concurrent work is, okay, so we can actually rewrite into a polite theory, but this is not in the paper. So this alternative would actually help us lifting the disjointness restriction. Okay, so politeness. What is politeness? So it's this method to have modularity, so to have a decision procedure for satisfiability in the combination of theories from decision procedures for satisfiability in each independent theory. And for that, you still have, as I said, the disjoint signature condition between T1 and T2. And then you substitute the Stanley infiniteness by the strongly polite restriction, which says, which basically is asymmetric, right? So you require this condition on T1 with respect of the sorts that are shared between the two theories, okay? While Nelson open is like a symmetric setting. And for a strong politeness, we only need a sufficient condition, which is if you give me a smoothness and you give me finite witnessability and you give me additivity, then I have a strong politeness. And so what is a smoothness? A smoothness is the possibility to increase arbitrarily the cardinality of the model with respect to given sorts. Finite witnessability would be I basically can compute. I have a function that given my formula, I can compute another formula where I have a model over the variables of the formula. And finally, additivity, basically, it's a condition that relates basically witness of basically you impose a relation between a couple of formulas here. So if I'm not mistaken, it should be these two, yeah. Where you say, okay, these two guys, this is a witness function, these two guys should be equivalent and they should use the same variable. And in our setting, it's gonna be a bit simpler because the really this formula phi here, which is a conjunction of literals, in our setting is gonna be at worst conjunction of equalities and disequalities. Okay, at least for the index one. Okay. Okay, so then I start basically with cardinalities, which is historically kind of the first theory in this family, and for which Bansal basically left open politeness. And basically, you have simply a theory that allows you to have sets denoted with letter B over there, and then you can take, where is it? You can take cardinalities, which are not here. No, yeah, they are here, right? So you can take the cardinality of the set, and then you can restrict this cardinality over here, right? Using inequalities, you can sum numbers and stuff. So one of the motivating use cases of this theory is to specify the data structure. So if you want to say I insert an element in the data structure, I want to specify how the data structure changes. So I can say, well, the set of elements contained in the data structure is going to be updated with E. Is just a set of size 1. And then if I have that the contents of the element was already in the data structure, then the length is the same or the cardinality is the same. And if not, then I have actually added something. Right? And this connects with the idea of modular verification where, okay, I have this specification, so now I can use these specifications and decision procedures for them to reason about more general programs. Okay, so how do you prove a smoothness in this setting? The idea is, I didn't say it, but here you don't have politeness always. You have to really use the relative complement because otherwise you are restricting. You could say that the size of the whole set is 3, let's say, and so you cannot increase the cardinality in the index domain, let's say. But if we use that theory, that version with relative complement, which was studied by Caballero Zarba, then it's easy to extend because you're not restricting so you have your Venn diagram and you have your sets, okay? And essentially you are not restricting this region here, okay? So the complement of all the set variables. So you can really add more indices and so you get a smoothness. And then you have, you have to prove finite witness ability, and that's more involved. Let's say you want to introduce these Venn regions I'm mentioning here, and then you want to kind of compute the minimum cardinality that you could get, and then you have to inhabit these Venn regions according to the computed cardinalities, and that actually yields a set of possible configurations. And then you output conjunction of this input of the input formula and this disjunction over all configurations. And in fact, it's not enough. You have to tweak a bit this definition to get additivity. So one of the things that we need to do, so at the bottom case, we really just compute the witness function that I showed in the previous slide. But you have to be careful. So you have to guarantee that your input formula is arranged with respect to the indices, because if not, then maybe you can increase the minimum cardinality, let's say. And then you have a couple of cases to make this additivity condition hold. So you say, okay, in the first case, if I actually get my W of phi here, so this is phi prime, it's the witness of some arranged input, which is going to be arranged. Then and I get a conjunction of literals, then okay, in that case I'm done. I don't have to do anything else, okay? And the second case is here where actually you have variables that do not occur in this part of the formula, and in that case, okay, they are not really relevant to the satisfiability problem, so we just can put them outside, let's say, of the function application. Okay, so that gives you additive finite witness ability, and with that you get the strong politeness of Zarba's theory. Okay, and back to the beginning where we were talking about these arrays, right? So we are back to arrays, and here you have the map operators that I was talking about. You have also writes and stuff. And maybe an example to motivate this theory, you could say you can specify transition systems, because really this is a restricted kind of regular relation. So you could say, okay, my system is specified by array A, and then at position 0, I have some state, and then I have the property that in every position of the array actually have some validity condition, and then at the end I get that basically I at some limit or position I arrive to some final state. And the nice idea would be that, okay, if I have theory combination, I can combine with a specification for the states, right? No matter what they are. So I can restrict the initial final states. And so in this case, you have to operate with both index and element sorts. Smoothness is quite easy for the element sort. For the index sort, you have to, do like kind of a two-side argument. So here you fix element theory and you show that you can increase cardinality of a model for the index size. And you do that simply by sort of copying some solution that you already had in the given model A. Then we have finite witnessability. So there it's somewhat similar to the decision procedure. So what you have to be careful with are negative relations. So if you have the negation of this relation, which is axiomatized with a universal quantifier, then what you're really doing is essentially a lemization. You are producing a fresh index I where the relation, the negative relation in the element theory, as I don't confuse these two symbols, so in the element theory holds. And then once you do that, you simply have to massage a bit the formula. So you have to introduce explicit variables so that the model happens in the variables of the formula. And then, so there are some technicalities about basically how the proof is sketched, but that's basically the idea. It is very simple because in this specification we don't have things for elements or indices, so this guy is empty, and so the condition really reduces to some kind of idempotence, right? So you have to relate these two formulas. And then you get the strong politeness for combinatorial array logic. And so then, how are we doing with time? Okay, yeah, plenty of time. So then the final situation, the final theory we consider is this idea of having set interpretations, right? That I mentioned at the beginning. So, and mix it with BABA, right? And so these theories are surprisingly used in probable scenarios. So one of the nicest scenarios where this use is when they want to specify consensus protocols. And so this is actually taken from a paper about this kind of distributed computing verification, where you kind of have to see whether the set of protocols that have some value are more than 2/3 of the population or whatever. And so this is one example of application. And here we have to be a bit more careful. So this falls in the second goal that we set, which was to really see how far can we go. And it's a bit technical, in fact, to get a smoothness, because in this case, you have set interpretation. So this region over here is going to correspond to the negation of set variables, but set variables are interpreted. So what you get is essentially some condition, right? So over here, right? Negation of the formulas that appear in the set interpretations. And if that formula turns out to be not satisfiable, then you cannot put your indices here. And so what we did to fix that was to say, okay, let's call this formula some kind of closure of the formulas that appear in set interpretations. And then we have the TF theory. So this is F because it's the theory called flat array fragment. Okay. So TF, when you fix these formulas, is going to be essentially the set of sentences such that they are true, assuming that this closure formula is satisfiable. And so that ensures that you cannot have an actual theory, so it's closed under propositional operations. If you do that, you get a smoothness for the original flat fragment with respect to the element sort. If you fix the formulas, then actually you get with respect to the LM and index sort. That said, I have the impression that people mostly care about the smoothness with respect to the index sort, with the element sort, sorry. Okay, so then the argument for final witnessability is really similar, again, to the decision procedure. And you just have to be careful to basically, when you do the Venn diagram decomposition, with which some of you are familiar, right? When you have these set interpretations, you have to remove those regions that are empty because the corresponding formula in the set interpretation is unsatisfiable. Okay, but otherwise, the procedure is really similar to the BAPA case. And yeah, so additivity works the same way. And so we get the strong politeness results. Okay, so in conclusion, we basically updated the idea of these modular decision procedures for array theories to the parametric setting, where you have some form of universal quantification. And I think the key ingredient to do this in a not very painful way was that in the time between the original polite paper and our work, people actually developed things like additivity. So that actually simplified the proofs a lot. And hopefully we can, I think, two kind of interesting properties of these theories. So these are simple models, let's say, but people really study all sorts of extensions. So hopefully this helps in having these rich classes of constraints over arrays, in particular for properties that pull component-wise, but also something that at first is not surprising, but actually people like it, is the fact that we have theories that work over arbitrary data types. Okay, and with that, if you have any questions, I'm happy to answer.